A very popular theory for statistics is called the central limit theorem. This theory states that if a sufficiently large sample is repeatedly obtained from a population, the mean of all the samples will be approximately equal to the mean of the population. In addition, if plotted, all of the sample means will follow an approximate normal distribution pattern, with all the variances being approximately equal to the variance of the population divided by each sample's size. This is called the standard error. This theory also states that there are no limitations regarding the shape of the original distribution.
You mean regardless of the shape of the distribution?
It could be normal, it could be rectangular, it could be skewed. The shape doesn't make any difference.
So if I drew repeated random samples and plotted those characteristics, we would get a normal distribution.
Correct. We can check the validity of this theorem by doing precisely what it says and noting the result with a simulation.
We will do exactly that. We'll go to Rice Virtual Lab in Statistics. The URL is presented for you, and we'll have different populations. We'll draw different sample sizes, and we'll see what the distribution of the sampling distribution looks like when we draw samples of various sizes from various populations. We'll do it from a parent population with a normal distribution, then with a skewed distribution, and then with a rectangular distribution to illustrate the central limit theorem. Here we've landed on the Rice Virtual Lab in Statistics Sampling Distribution homepage. So let's begin by looking at our distributions. We'll click Begin. Notice now here we have the parent population. It's normally distributed. We want to look at the sampling distribution of the mean. We'll have a sample size of 5. And down here we'll do the same thing. We'll look at the sampling distribution of the mean, and the sample size is 25. Importantly, as you look up here, you'll see that the mean of the population is 16, the median is 16, and the standard deviation is 5. So now we're going to draw samples of size 5 and samples of size 25 and see what the distribution looks like. Recall, what we'll do is we'll draw the sample, calculate the mean, then plot that mean. And we're going to do that, notice here, 100,000 times. Well, we won't do that. We'll have the machine do it for us 100,000 times. So we'll click 100,000. Look at the shapes of the distributions. Notice the measure of central tendency, the mean, is very close to 16. In fact, if you look here with a sample size of 5, the mean of the means, the mean of the sampling distribution, is 16. And notice if the sample size was 25, the mean of the sampling distribution is 16. Let's change the shape of the distribution. Let's change it from normal to skewed. Notice we have a very positively skewed distribution. We'll leave everything else the same. Notice that the mean now is 8. The standard deviation is 6.2. Let's draw our 100,000 samples and see what the shape of the distribution looks like. Notice that the parent population is very positively skewed. Here's our 100,000. Notice the shapes of the distribution. Here's with a sample size of 5. Notice what the mean is. The mean of that distribution is 8.09. Very close to the 8.08 of the parent population. Look at the mean when we do a sample size of 25. The mean is exactly equal to what we found from the parent population.
And notice that the sampling distributions look very normally distributed.
Let's change it one more. Let's get a very unusual distribution and see what that might look like. So let's go and let's create a custom distribution. Let's make our own distribution. In fact, let's make it look pretty much like a rectangle. So we'll create this rectangle, and then we're going to see what the distribution looks like when we draw samples. Notice with our rectangular distribution, the mean is 14.5. Standard deviation is 8.08. Let's take our 100,000 samples. Let's see what the distribution looks like when the sample size is 5 and then when it's 25. Remember, the parent population is rectangular. 100,000 samples. Notice once again, regardless of the shape of the parent distribution, when you randomly sample, you'll get a very normal distribution when you plot the sampling distribution of that statistic. Here we've calculated the sampling distribution for the mean. We could have calculated it for the median, the standard deviation, the variance. You are encouraged to go to the Rice Virtual Lab in Statistics website. There are many simulations that you can work with. In this particular case, you can enter the distribution and see what happens to the various sampling distributions. You're encouraged to practice it to better understand sampling distributions.